Today, I'm going to talk to you about the hallmarks of science. Now, the hallmarks of science is not really agreed upon like universally. It's a set of rules that a hypothesis has to make or adapt to before it could become a scientific hypothesis or go through a scientific process. But for the most part, not everyone, has a set of rules for what a hallmark of science is. But uh, Mr. Hewitt and I have categorized it into basically three pillars. The first is natural, the second is simple, and the third is testable. So let's go through one at a time. Natural. Basically, you're thinking of plants and animals, trees, and whatnot. But what we mean by natural is not supernatural. That's literally all we meant. So Michael Shermer says it the best: before we say something is out of this world, we should first make sure it's not in this world. Here's an example. What is that? Well, to me, it looks like a Yeti. And Yeti is not a real thing, though, for the most part. I mean, it doesn't have a biological taxonomy associated with it. There's no clear evidence of it. And why are the pictures that take a picture of these creatures, quote unquote, why are they always fuzzy? Well, anyway, this is obviously you can think of this as just a Yeti or Bigfoot or some creature of the unknown, but it's best to first think of it in terms of natural things, things that we've already known and discovered. More than likely, it is just either a person in a heavy bear suit or some furry suit, and somebody just wants to take a picture to put it in the World Weekly, World News, or just to troll the internet community. So more than likely, it's a fake photo or just a photo that trolls. It's not a real thing. That's just because we want to try to go stick with the natural philosophy before going into unnatural things. The second hallmark of science is simple. Um, with that comes this thing called Occam's razor. Basically, if you have two ideas that talk about and identify and describe a model equally as well as each other, you should always take the simpler model or the simpler explanation. Now, the reason why is not because you just want to take the easy way out. That's really not the reason why we use simple as a hallmark of science. We use it because statistically speaking, it's more likely that a simpler explanation is correct. A good example is, with engineers, they prefer fewer moving parts. That's why a helicopter took off, no pun intended, as an actual design infrastructure for a flying object, but not the quadricopter, which has four blades. And the reason why is because the fewer moving parts, the fewer things that can go wrong. Now, the same thing goes with the hallmark of science of simple, and especially with Occam's razor. If you have fewer logical bridges to build between a premise and a conclusion, you have fewer things that need to be explained in order for that bridge to hold up. So another example would be the heliocentric model versus the geocentric model. Now, it seems easy that if the sun goes around the earth as it appears to us on earth, that in reality, the sun really does go around the earth. I mean, that's really easy to talk about and really easy to think of. But think about the logical bridges you have to build to get there. Well, for one, if the sun is a lot more massive than the earth, how is it that the sun is rotating around the earth and not vice versa? So that's a logical bridge you have to build. Next one is, well, why is it only for that case but not for other cases? How come the moons of Jupiter go around Jupiter but not the other way around? That's another logical bridge. And you got to build a lot more in order to explain that. But if you say that the earth goes around the sun and the earth's rotation is the reason why we're seeing the sun go up and down in the sky, there's really only a few logical bridges and they're all pretty ironclad. Here's a little funny thing also about why we want to take a simple approach to scientific hypothesis. Here's a mad scientist saying, well, to be perfectly clear, in my humble opinion, of course, without offending anyone who thinks differently from my point of view, but also by looking into this matter in a different perspective and without being condemning of one's point of view and by trying to make it objectified and by considering each and every one's valid opinion. I honestly believe I completely forgot what I was going to say. Well, that's something that we want to avoid. Political correctness. Scientific correctness is not political correctness. Now, we're not saying that it's bad, but we're just saying that in the scientific community, we want to be correct more than anything, even if it offends people. So that is also something we want to do. We want to be simple. We want to be correct. We want to be discreet, and that's that. The third hallmark of science is testability. Basically, when you think of testability, you're probably like, well, how does anybody have the ability to test most things in science? Like if I ask you, hey, why don't you test the speed of light? You're not going to be able to do that easily unless you have some background in the theory and whatnot. When we mean by testable is we have the physical capacity to test it, assuming we have the financial and the mental resources to do it. um, Testability just means that we can physically do it. Okay. So anyone can test the speed of light if they have the education and the finances to do that. Everyone can test um, what the moon is made of if we have the finances to build a rocket and the ability to understand space mechanics and whatnot. So these are all testable claims. Like we can go to the moon. That's testable. The speed of light is almost 300 million meters per second. That's all testable. Now, with that comes a notion of falsifiability. Falsifiability is actually very important, and I believe maybe 10% of you are still going to get this wrong because it is kind of a mouthful. It's a very counterintuitive concept. For something to be scientific and, of course, to be testable in that process, it has to be able to be proven false. If you can't prove your hypothesis false, like in no way can you prove it false logically, you don't have a scientific hypothesis, you have an opinion. Um, Charles Darwin himself said with his theory of evolution, if organisms get if organisms get simpler um, as time goes on, that means that his theory is incorrect and needs to be modified. That's a falsifiability statement. Let me give you an example. Intelligent life exists on other planets. Is that scientific? First thing you want to say is probably yes, intuitively, it makes sense. You can prove it right by finding an alien, but can you prove it wrong? Well, let's see. I go to the planet Mars, try to find the alien. I did not find the alien. Well, what's the excuse? Oh, I just didn't look in the right place. Obviously, I know aliens are on Mars. They could be on Jupiter. So I spend years the best building the best satellite that can withstand the pressures of Jupiter and can go there within a certain uh, reasonable time limit. I go to Jupiter. I was able to analyze um, everything there, and I found that there were no life forms, no intelligent life forms. Did that prove anything wrong? No, it just means that there must have been an alien, not on Jupiter, but maybe on another galaxy. And you can keep on going all the way to infinity. So this inability to prove the existence of aliens incorrect means that the statement that aliens exist is not scientific. If you like Venn diagrams, have I got a treat for you? So here is a scientific claim: confirmed true, confirmed false, and falsifiable. Those three are scientific claims. If your hypothesis or whatever you come up with, your statement, falls into any one of these categories, it's scientific. Otherwise, it's not scientific. Here's an example. Aliens exist. Remember, we just talked about that. Well, right now it's not it's not falsifiable, so it is not scientific. However, if somehow we find a extraterrestrial life form that's intelligent and is considered an alien. We have just confirmed it true. It was never falsifiable, but since we found one, we've confirmed it to be true. Now it's a scientific claim. So yeah, something can previously be non-scientific and then become scientific later. Well, that basically wraps it up for this particular piece of the lecture. The hallmarks of science: natural, simple, and testable.